Okay, so this is the second video. So we're going to actually get into Physics 1112, the second semester. And to do that, we kind of want to review the first semester and note that we're kind of happy that we learned what we learned in the first semester because we're going to be using those things in this second semester. So I'm ready to do that. Let me get my, you'd think I'd have my piece of paper already over here, but so here's the review, and it's not quite as lengthy or as in detail as the review we did for the comprehensive final last semester, but it's still going to hopefully refresh you a little bit and help you think about, in your brain you're going to go, oh, that is something I need to bring up to the surface again so that we can get things right this semester. Hopefully you will do that. And keep in mind, just about every single thing that we did last semester is going to be applicable, but I'm going to cover the highlights. Okay. So why do we study physics? It's so that we can understand nature / reality so we get to understand nature and reality with physics, and the key there is knowing that we're never going to quite get the full picture of nature and reality. So we do things, we experiment, we come up with theories, we use the scientific method is what I'm explaining right now. And that allows us to predict outcomes or behavior of systems. That allows us to anticipate the consequences of certain actions, which everyone enjoys, anticipating the consequences, and then sometimes you get unexpected consequences, but hopefully they're positive. Okay, so that's the whole reason for doing this. We have things to learn, and so here's what I'm going to say. The thrust of this class is electromagnetics. So how is that going to relate to what we did last semester? Well, that's what we're talking about now. Okay, so last semester we initially started talking about physical quantities. And the physical quantities that we measured last semester, just keep in mind electromagnetics there. Physical quantities from last semester were, we had mass, we had length or distance, we had time. These were really the only things that we could measure with our equipment. Every single thing else came from measurable. Everything else that we came up with, velocity, energy, you name it, torque, doesn't matter, force, torque, all of those other things were calculated, or they call it derived, from these measurables. Okay, so the nice thing that we're going to do next is add a couple of things. We're going to add in a physical quantity that's a measurable, and for PHY1112 we are adding in I. It's not the moment of inertia anymore. You can kind of forget maybe a little bit about the moment of inertia, or at least its relationship to the symbol I. Moments of inertia are still out there, and yeah, you still use I for the symbol, but this semester our I will be current, electrical current. And so here, let me do the units for these guys. This unit of mass, everybody should know, is kilogram. The unit for length is meters, and the unit for time is seconds. So we learned last semester that the System Internationale SI system that we use also has another name. So SI has another name. MKS. That stands for meters, kilograms, and seconds. Okay, so in the MKS system, we have an electrical current, and it has an A. The A unit is equal to an ampere, named after a famous physicist who was working a lot with current, electricity, and all those things. And so ampere came up with this stuff, and in the end we came up with an electrical current that holds his name. So we now have measurable quantities. We now have 4. We have mass, length, time, and electrical current as part of our MKS system. So just on a side note, MKS has a competitor called CGS. The S still stands for seconds, but the C stands for centimeters, the G stands for gram, and S, of course, stands for seconds. So it's a centimeter gram second system. So kind of technically, it's still an SI system. Okay, and so even though it's SI as well, we want to still hold to our MKS version of the SI system. And there are conversions, of course, between back and forth. And so an amp in CGS is called a biot, which is a name for another famous French physicist who, well, at any rate, he did a lot of things with current as well. And ampere, and bio, they both, I don't know, let's just say that because MKS is the dominant system, ampere is somebody who is more recognized. So what do we have? We have we have to do a conversion. So let's do that now, since I'm here. 1 BI for bio is equal to 10 amps for amperes. And of course, we learned that we can turn that into something that we can multiply anything by 1, and we can convert and get the right thing depending on which thing that we're looking for. I'm giving you this, we're not going to use bio a whole bunch. I don't know if we ever will, but what I'm doing is trying to explain to you that we have the MKS system that we're going to use mostly, and there are other systems, of course, and those systems have their own units for current. And this is one example. So most of the time, oh boy, sorry about that. Most of the time we're going to be doing simply doing amps. So amps is the way to go, and that's an A. Okay, so let's get back to, we had calculated and derived, so there are measured quantities and then we have calculated, so versus calculated quantities. Okay, so measured quantities versus calculated quantities. Before we learned that speed is a calculated quantity because it's equal to the length that we can measure divided by the time that we can measure. Okay. Density is another one, right? Mass per length cubed. But we're learning some things about electrical currents and electromagnetics. So we want to do 1 amp, which is measured. So we can do 1 amp. And that is equal to let me do this a different way. 1 amp, I keep wanting to erase with the hand. Sorry about that. 1 amp times 1 second, so both measured quantities, is equal to 1 charge, 1 coulomb. So how we say that is we have our current I, and we're multiplying that by time, and we're going to get our charge Q. So Q is a calculated quantity. Now, this is true. It's very true. However, you can measure an electron's charge straight away. So this is one of the things that, even though it is calculated, in our case, we're going to be doing this. We're going to measure our current, and we're going to measure our time. That the current flows, and when you multiply those together, you're going to get your the amount of charge that went through in that amount of time. We're going to get into the bottom unit of charge later, but this is also a measurable thing. What happens is you measure so many of these that it's like measuring atoms. You kind of have to go to a mole, and so when you're measuring atoms, you end up saying, oh, well, I just have a whole bunch of them, and that is our Q. So that's E times, who knows, billions, 10 to the X power, however many there are. So that gives us our Q. So, okay, hopefully that wasn't too, that was clear, hopefully. Obfuscated. Obfuscated means to muddle something. All right. So we can measure electric current. We've got time, and we know that Q is the calculated or derived quantity. Great. And we know that we're going to be working with the MKS system. Which gives amp as the current unit. So let's do a little bit more here. Let's talk about significant figures. We learned before that if you're given a number with 2 significant figures, 3 significant figures, and 4 significant figures, that the one with the least amount of significant figures is the one that you have to use. So that ends up meaning that we really only have 2 significant figures. That's the limit. This is the limiter right here. If this wasn't there, then, or if this was a 3, then we would have 3 significant figures, because 3 would be our limit. So at any rate, you need to keep that in mind. Don't give me too many significant figures, or you'll miss out on some points. But for our class, the best way to answer a problem, let's say the answer is 345 times 10 to the 5 amps. That's a lot of amps. Equals I. If that is your answer, you're doing the right thing. you're saying I have 3 significant figures, which is the scientific notation. You're giving me the order of magnitude, and you're saying what it equals, and you're boxing it all in. So this is the proper way to show an answer. Good. They called this scientific, S-C-I-E-N-T, scientific notation. And I think I talked about this last semester, but for those people who aren't here, the reason is here we have the hundredths of something. This piece is the hundredths. Anything much further below that is just not significant, right? So we have 10, 100, and 1,000. If you're less than 1,000th of something, it just doesn't, 1,000th doesn't really mean much. So let's say you're given 3.42 times 10 to the, 3.427. Okay, times 10 to the 5th. That's our number, okay, for amps. What do we do in this case? We take anything that's 0 through 4 and we don't do anything to it, the previous digit. So that would leave the 2 unchanged if it was 0 through 4, but it's not. It's part of the group between 5 and 9. So then we bump up the digit before. So since 7 is larger than 5 and less than 9 or equal to 9, we pump up and we make that 3.43 times 10 to the 5th amps. Okay, so this is how we round up. And that's why we do it, because that 7, if you were to divide 7 times 10 to the minus 3, if you divide that by 3.427, and we multiply that by 100%, where's my calculator at when I need it? Come on, calculator. Okay, 7, 10, oops, minus 3. And we're going to divide. You'd think I would be able to do this really quickly. 3.427. And we're going to multiply by 100, so we get the percentage. That is equal to 0.2%. And that is just not enough to worry about. It's going to lie within our error. Any experiment that we do, we're going to have a plus or minus something, our DI in this case. That is, if that is much larger, it'll be probably around 5% or so, let's say. So 0.2 compared to 5% is nothing. So that's why this 7 doesn't matter. We don't care about the 7. And so we round up to the 3, and we get a nice number that is totally fine. So, okay, there's a little stats for us and our laboratory stuff, which I'll be covering more of on Monday. We did the unit conversion stuff, so we can move on from there. What did we do a lot of last semester? Last semester, we really hit hard on trigonometry. So I'm going to draw my typical right triangle. We've got our hypotenuse. We've got the opposite side to the angle. We've got our adjacent side. What the heck? We've got our adjacent side to the angle. And then we've got the relationships. So let's do those. We've got the sine of theta is equal to the opposite over the hypotenuse. We've got the cosine of theta is equal to the adjacent over the hypotenuse. And then we've got the tangent of theta is equal to the opposite over the adjacent. Okay, now all of those things get flipped around if we were to do the same thing for phi. And you can look at it from phi's perspective as well, but then you just have to flip these things around, okay? And the opposite becomes the adjacent at that point, and your cosines become the sines, and you get the picture. So from these equations, we can do a little algebra, and we can start seeing that the hypotenuse times the sine of theta is equal to our opposite side. Our hypotenuse times the cosine of theta is equal to our adjacent side. And our adjacent times the tangent of theta is equal to our opposite side. All of these things help us break vectors down, because you're typically given this hypotenuse vector, and that hypotenuse vector often needs to be broken down into its coordinate system. So you want to get this adjacent side, and you want to get the opposite side so that you can do your x and y breakdown of a hypotenuse vector. And then you can do things like add other vectors to it. So this is how we do that breakdown. And then lastly, if you want the angle itself, then you can do the arc sine of the opposite over the hypotenuse. And you can do the arc cosine of the adjacent over the hypotenuse. And you can do the tangent, arc tangent of the opposite over the adjacent. Okay, well, that is the nuts and bolts of trigonometry. There are a few cases and times when, we end up with double angle formulas and and some of that stuff. We found a few instances last semester where that happened. But for the most part, this covers us pretty well in what we need for trigonometry. So we were talking about our orthogonality and the orthogonality between x and y. And so that's still a huge thing. It's still something that we use as a tool. And that tool comes from, so orthogonality, this is why I'm not good at Wordle, because all my words that I know are far larger than 5 letters. I'm always trying to, that's a nice word. Oh, and it's way more than 5 letters. Okay, so orthogonality, that just means perpendicular. Things that are perpendicular to each other get this symbol. Orthogonality, when we define a coordinate system, we want it to be orthogonal so that the y, anything in the y direction, has no impact on what happens in the x direction. And that allows us to add and subtract vectors, to add and subtract vectors that are electromagnetic vectors, which we'll be doing, force vectors that stem from electromagnetic forces. So many things that are going to be popping up in our future. We need orthogonality, and that's why we define orthogonal coordinate systems. This one happens to be a Cartesian. I really should put a capital C on there because it's based after Descartes. So Cartesian coordinate system. He did maps and such, so we gave him some credit there. And then that allows us to apply our right angle trigonometric functions that we just discussed. So, good. Yes, the electric field is a field of vectors and so since it's a field of vectors, just like the forces that we would do when we would sum up forces, well, that's a horrible sum. There. Believe it or not, this is the best software I could find. Maybe I need to splurge and get something. Okay. So, the sum of the forces, which is basically a sum of vectors, was equal to MA, and we found that. Well, the electric field also is a field of vectors, and we're going to be adding those vectors together as well, and we'll have equations and such to go with that. So this is just standard stuff, and that's why we learned it so well in the first semester. Okay, so now that we're talking about that, let's do an example for those of us who forgotten or are rusty. Who knows when some of you have last done these things. So we're going to have a vector A. We're going to add that to a vector B. And we're going to get a resultant vector R. So here's our vector A. Here's our vector b. And we need to add those together. What do? We use the head to tail method. We have to draw out our coordinate system. We're going to start with A. So I'm going to pick up A and I'm going to move it to right here. There's A. And now I'm going to add B to it. So I pick up B and I put the tail of B on the head of A, and I get a vector like that. And the resultant is what we get from the origin to the head of B. So this is our Y, this is our X, and that gives us an R. And if I pick up R and I place it down, I get that. So A plus B equals R. And then, of course, if you were to do A minus B, you just flip B around, and you have a B that looks like that, and then A minus B would give us something like this, and then our R would be here. Okay, so this is R plus, and this is R minus. All right. By the way, this symbol on top of any number or letter, value, whatever, that is the symbol for a vector. And if we were to take the average of something, there's no arrow. It's just a bar. So that's an average. Okay. All right, so we've done that. Nice. Now, analytically, why did you slide over? I want you there. Okay. Analytically, what we've done essentially is we've taken A and we've broken it up into its different components. So we've said A has an X component and a Y component. And then we've taken B, and we've also broken B up into BX and BY. So we can take and do all the X's and all the Y's independently. And it turns out that BX is negative. So we're going to subtract in the X direction BX, and we're going to be adding in the Y direction BY, and that's going to give us our resultant X and our resultant Y. And then we do all the neat tricks that Pythagoras taught us, and we can take and get the magnitude of R equal to Rx plus Ry squared, square root. And that angle, let's call it theta. The angle for R, theta, is equal to the arctangent of Ry over Rx. The one in the denominator is the axis, so X is the axis that it's with respect to. So we want with respect to the x-axis, with respect to. Okay? Okay. So we've been talking about vectors because that's what trigonometry is all about. But what else is out there? We've got scalars and vectors. So scalars and vectors, we know that force is a vector, acceleration is a vector, delta x is a vector, even though position is not, the length of something in a certain direction is. So that is important to keep in mind. Electric fields at any point, so let's say we have an electric field, at this point it has a vector. Let's say it's straight down, and so at this point right here, the vector for the electric field points down. It is a vector. And so the field is a field of vectors. And depending on where you're at in the field with relation to the charges or the current, you'll have different vectors. Okay? So it all depends on what point you're dealing with, and then the length of the vector as you've drawn it represents the magnitude of the field at any point. So at some points the field will get larger, some smaller, and so we represent that with the length of the actual vector. But it's simply nothing more than the magnitude of that thing. Okay, so everyone's freaking out because, oh my gosh, electric fields, I don't know what you're talking about. You're blowing my mind right now. But this, let's say, is the Earth. We're going to call it big M, mass M. And here is a satellite. And that satellite has a gravitation. There's a gravitational field, and that field is always pointing in. And as we get further and further from the center of mass of Earth, there's the center of mass, right in the middle. As we get further and further from there, the gravitational field decreases. And we can all kind of see that. Oop, I made a mistake. And this is all in the R direction. Okay, so the field points inward, and as you get closer to Earth, that field increases. Okay, so it has a bigger vector and a smaller vector. So here on the surface of the Earth, g is 9.8 meters per second squared. Out here, it's less. It's, in fact, after you get far enough away, it's 0, right? So this is a vector field also. It's the same thing. We're going to be using this same thing for electric fields. In an electric field, you'll have, say, a positive charge, and you'll have a negative charge. So we call that Q plus, and this one Q minus. Let's move this up a little bit. And our gravitational field will, that Q minus fields will be the electric field. This isn't quite the right nomenclature symbolically, but I'm going to just write it like we did so our electric field is going to look like this in the R direction. Okay, the actual force, just like in gravity, the force, you have to add in the m. Now you have a force, the mass of whatever the object is. So we're going to add in, we'll have our k, we'll add in our q, q minus and q plus, and then the distance between them. So it's a very, very similar thing, only now we have plus charges and minus charges. So nothing really is changing. It's just that at some points in time, the field is larger or smaller. So at this point, the further away they are, the smaller the field. If Q minus is here, it's going to have a bigger field. Okay, a stronger force. It's the same thing. Okay. Great. So, we've learned how to add and subtract vectors, and we can do that, and we can come up with what the forces are going to be at certain points. This equation here we're going to learn about. This is called Coulomb's law. Do you guys like my handwriting? I'm trying to do it without putting my palm on the screen. Okay, so that's Coulomb's law. We're going to be talking about that. We're also going to be using concepts like static equilibrium, which you guys learned about before, and we kind of beat it like a dead horse. We've got our alpha here and our acceleration. So here's our rotational acceleration. Here's our linear acceleration. Both of those things can't be equal, must be equal to 0 for static equilibrium. There I go again, sorry. Okay, which means our charges, these charges here, they aren't moving. they're just sitting still or held in place or what have you, but A and alpha are equal to 0 for those in a static equilibrium condition. So we learned about that. All of Newton's laws. We learned about those quite extensively. Those laws still apply, and let's just say that they still apply. All the forces that we learned about, and I kind of gave you a clue into what the normal force is. Normal force last semester is nothing more than the electromagnetic force. And we'll talk more about that. Frictional forces. Before we do that, let's do tension. Tensions are still there. We have tensions. Spring forces. Tension, spring force, sliding and rotating. Slide means translation, or moving in a straight line. And rotating means revolving. What did we use? What was the other term? I can't think of it. Okay, well, at any rate, all of those things still apply. But then we also had frictional forces. And among those are, oh, that's not good. Drag and other assorted surface frictions. So those are still going to be there. And I think this is a good point to stop our second video. So I'm going to end video 2. End video of, no. End of video 2. Okay, thank you guys, and I'll have another one posted shortly.